Okay, today there are another 5 problems that we're going to discuss, and this is going to be the last uh, online practice contest we're going to hold during this summer. We'll take a 1 week break, and then after that, we'll be back on campus and we'll start organizing in-person sessions again. All right, the first, sorry, the first problem, it's less versus fewer. So basically, they're telling you that certain nouns are either a count or mass noun. And to make things grammatically correct, you can say number of days, number of something has to be countable. You can't say number of water, and so on and so forth. And so they tell you that these are the different things you have to check for. Um, and then you have to say yes or no, uh, correct or not correct. Okay. So it starts with a certain number of nouns, then they tell you whether each one is a count noun or a mass noun, and then there will be things like this. So basically, if you look at all the rules here, you can actually just look at the first word to figure out which one of these phrase it is. Sometimes there'll be a middle word, the off. Sometimes there won't. And then basically, you just want to look at the first and the last word. Um, and then apart from that, there's not too much more to say. Um, Of course, you can write it in a more compact way or a less compact way if you use an if then else, for example, for each one of these. That's certainly possible, but then it's a little bit more, I don't know, maybe a little bit more work to write. So let me just straight away run into what I do. So at the beginning, I store the nouns into two sets, C and M, counts and mass. And so I use sets of string so I can look up later on for each string, for each noun, whether it's mass or count. There are other ways you can do this. You can have a map that goes from a string to a Boolean. So you can map, I don't know, noun to true if it's a count or whatever you want to do. Okay, so I just decided to use two sets, C and M. And then I'm going to read one line at a time. And again, this is something that I mentioned before because I was reading with this extraction operator with double arrow. When I'm finished reading, I would be left hanging at the end of the line. So I need to do a C and dot ignore so that when for the next inputs, when I start reading line by line, get line, I will be in the right place. So for example, oops, hang on, my pen is in a funny place. I need to change my touchpad setting. Uh, Here, map to the other monitor. Okay. All right. So let's do this now. Okay. So if I look at the input here, when I go C in arrow, arrow, noun, and then type this, it's going to read the noun, it's going to read this, and the cursor is going to stop right at the first spot that's no longer a string. And in this case, it's basically a space. Then it's going to read the type, and then it's going to stop at the first spot that's no longer a character. And then it's going to stuck at this hidden new line. So if next time I just get line like this, it will read the next line up to the next new line, but you're already at a new line. So just say, oh, I'm going to read a blank line. And so you'll miss what you really want is to read the next line. So in order to do that, I will do C and ignore one because in programming context, you can always assume that the input will not have any strange invisible space. So you know that it's always going to be a new line. So ignoring the next character would move you a new line, and then get line would be giving you the right lines. Okay, so that's something here. And then for each of the P phrases, I call check. And then it will tell me whether it's good or bad. So check, what do I do? So I'm reading the line with get line, and then I'm splitting it up with iString stream because there could be 2 or 3 words, I don't know. And what I'm going to do is I'm going to read the first word. If there's a middle word, I'm just going to ignore. And this loop basically just keeps reading and replacing the last word until I can no longer read one. So when this loop stops, last will contain the last word in this line. And then I have this complicated looking statement. So instead of using if then else, what I'm going to do is I'm going to just store in a table. So in this case, a vector, which of the first words in the phrase can I have either one? Okay, so if I see both, so if I see either most or more, then I actually don't even care what noun is coming because everything is good, both um, count and mass. Or if I check if the first word is any one of these and the noun that you give me is a count, that's okay. Or if it's any one of these, it's a first word, and the noun that you give me is it's a mass. So how do I do that? Sort of 3 conditions. Either, so I call find, it's an STL command. I find in this vector both first, so it's a begin and end, and I'm trying to look for the first word. If it's not the end, okay, so find in STL will return an iterate to the place where it's found, or it will return the end of the container or the end of the range that you're looking for when it's not found. So when I say not equals to the end, it means that it's found. Okay, so if the word it's found, that means it's one of these. That means you don't even care what the count is, what the noun is. Otherwise, if you find it in the count list, so if the first word is a count list, and so this is to find that the noun, the last word is in the C, which is a count nouns list, a set, then I'm also okay. And then similarly, I have another check for the mass count, the mass nouns. So I check any one of these conditions. If any one of these 3 conditions is satisfied, it's okay. Otherwise, it's not okay. Now, you can, of course, not write it like this. You can write it as if, if this is true, then return true. And if this is true, then return true. And then else, if this is true, returns true, and so on. Otherwise, returns false. So you can change this in if then else statements. But that's the way that I find most compact and easier to write. Okay, so this problem, you can do it in many different ways. This is my way. So let's look at the next one. Actually, let's not look at this one yet. Let's look at this one first. I think this one is a little bit easier. Okay, so there's a numbering system to represent numbers with sets. So 0 is just this set, empty set. 1 is the empty set containing 0. 2 is not the empty set, the set containing 0. 2 is the set containing 0 followed by 1. And 3 is the set containing 0 followed by 1 followed by 2. And when I say 0, 1, and 2, we're talking about the representation. Yes, 0 and 1 and 2. And so you are going to be asked an input from 0 to 9, 0 to 8, and you have to produce the correct string. So actually, it's relatively straightforward, I guess, because if you know what is the string for any number up to n minus 1, then to get n, you just take all the previous ones, concatenate them with the commas in between, and then throw a pair of brackets around it. before and after. These strings do grow very long, so that's why it only goes up to 8. But other than that, it's relatively straightforward. The only thing that you should make sure is that you don't recompute it every single time. Because if you want to compute what is 3, then it requires 0, 1, and 2. And then to compute 2, you compute 0 and 1. So you might end up trying to figure out what 0 is all the time or 1 many times. But if you just remember what they are every time you compute it, then it's pretty straightforward. So I'm just going to just jump straight to the code. Okay, so I have an answer for all the inputs from 0 to 9, 0 to 8. Answer of 0 is just initialized that way. If you want, you can even initialize 1, 2, and 3 because they gave it to you. But anyway, there's no point doing that. So I'm just going to run a loop that computes all the answers from 1 to 8. I start with an opening brace. I ends with using concatenation and with a closing brace. And then in between, I just take all the numbers from 0 up to n minus 1. And then, so here I basically decide whether I want to add a comma. And I add a comma whenever I'm not the first one. So the first one when I is 0, so this is a quick check to see if I is non-zero, because if you put an integer in a place where you need Boolean, non-zero is true, 0 is false. So this is saying if it's non-zero, that means if it's not the first one, then you add a comma. Otherwise, you don't. If it's the first one, you don't add a comma. And in any case, after you add or not add a comma, you just add the answer of that one to build up. So it's you have the representative of 0, comma, representative 1, comma 2, comma 3, and so on. And that's it. That this part here will build up all the possible answers that you care about. And then you just read whatever n is and then print it out. Now you could say, well, why am I building all the answers up to 8 if I'm only being asked 4? And I guess you could actually just stop earlier, but since the answers, the input is so small in all cases, I just didn't bother with that. I just built all the answers. Okay. Now I want to go back to this last minute. All right. So here, this one I need maybe a little bit more explanation. So it says that there are different number of problems, statements, themes, and then there are this many algorithmic methods. So, but then there's each of these A and B, the algorithmic methods and problem statement theme, are split into topics that are unique, that can only be used once, and then things that can be reused multiple times, called reuse. So the question is, how many different problems combinations can you get, right? All right, so let's actually look at this. Oops. Hang on. Okay, so we have A, unique, and A, reuse, and A, B, unique, and B, reuse. Okay, and let's just say that for now we have 3 things here, 4 things here, 5 things here, 6 things here. Okay, it's just an illustration. Now, first of all, things that are reusable can be done in all the different ways. So if you look at basically every problem is a theme, some A followed by some B. Any one of these 4 can go in here. There are 4 choices here. And any one of these 6 can go in here. So altogether, there are 24 choices. And it's okay to use them because they are reusable. You're not going to use up anything you're not going to lose by using these reusable things. What about these topics here, the unique ones? Well, if there are any reusable ones, so there's three topics, you can match it with any one of these, and it will be a different one, right? So there's three of these unique A's that you can match with any of these B's, but it's not six of them because you can only use three of them, as many uniques there are, because the A unique cannot be reused. Okay, so let me write it in a slightly different way. So when you're allowed to have reuse combined with reuse, there are 24 of them because it's 6 times 4. If you try to match a unique with a reuse, then it's just the number of unique. Okay, so it's just 3. Because if there's 3 things, A, B, and C, you can match it with any of the B reuse, but you cannot reuse the A again to match something else. Similarly, when there is a B unique and you try to match an A reuse, in this case, it's just 5, because any one of these 5 can be matched with the reuse. So the answer here is just 24 plus 3 plus 5, which is 32. Okay, but that's not the end of the story. Now, some of these numbers could be 0. And then what do we do? Right? If B reuse is 0, then this will turn into 0. There's none of that here. Okay, so that we just multiply A reuse times B reuse, it to just take care of itself, because 0 will just wipe everything, no problem. But here, we cannot just say that we can match any of the A unique to B reuse, because there is nothing to match. So we can only do this matching if B reuse is bigger than 0. Okay, so we can match it here. So what can we do? That means we have to match it here. So we'll take one of A unique and one of B unique, and we can match 3 of them. So A unique and B unique, you can get 3 of them. Okay, what about B unique and A reuse? You can still do that, but wait, you already use up 3 of them. So this becomes 2. So now when B unique and A reuse, there are only 2 left. So altogether, you can only do 5 of them. Okay, so when one of these or both of these are zeros, for the reuser, you have to be a bit more careful. So this is what we're going to do, right? So I'll just show you the code now. You just have to write it carefully. Oh, the other thing is, hang on. One thing I forgot to say. All these numbers are 10 to the 9, so about 1 billion at most. And because we're going to multiply 2 of these numbers together, it can be up to 10 to the 18, which is bigger than a 32-bit integer. So I have to make sure that I use a 64-bit integer to store the answer. Okay, so I type def long LL, and then I use long for all of the numbers. I read in A reuse, B reuse, sorry, A and B unique, and then A and B reuse. And then I do this. Okay, so if B reuse is bigger than 0, then I can just match all the A unique. And because I can match all of them, I will now set A unique to be 0, so I can no longer use them. Okay, so that's the case when I can have unique. Otherwise, I'm going to try to match A unique with B unique. But if whichever one is smaller, that's the number match. If one is 5 and one is 7, I can only match 5 of them. So I take the minimum, and I update the answer by this much, and then I decrease the number of unique A and unique B that I can still use. One of them will actually be 0, because then again, I just don't know which one. And then I do the same thing for B, right? So B, for all the unique ones, if the A reuse is bigger than 0, then I can just match them all up. Otherwise, I will match the minimum of A unique and B unique. It's possible that there's still A unique left that you haven't used from here. Okay, so that's why we do the match. And then finally, we add all the combinations of the reusable ones, and that's the answer. Okay, so this one is a bit of a combinatorics counting thing, but you have to be careful exactly what you can match and what you cannot match. I guess if in doubt, maybe if you're not used to thinking about it this way, right? So maybe you can say, well, if A unique and B unique, let's say, I don't know, 2 and 3, and then A reuse and B reuse is like, I don't know, 2 and 2. You can just give this sort of a number. So you can say A1 and A2 are the unique ones, and then maybe A1 or A3 and A4 are the reusable ones, and you can make something like this. B2 and B3 are the unique ones, and B4 and B5. And then you can sort of see how many different pairings you can do, right? You can do A1 and B4. You can do A2 and B5. But you cannot do A1 and B1 and so on after you've done use A1 B5. And there's no reason to do A1 and B2, A1 and B1, for example, because if you do like this, in this case, then you use up B1, which could have been you matched with A1 with A3, because A3 and A4 were usable. So then you kind of just say, okay, what are all the combinations, and you try to come up with a set that is as big as possible. You can actually reuse A3 every time, and then you can have all the different ways of A3, B4, A3, B5, A4, B4, then A5, A4, B5, and altogether you have 9 of them. And if you try to match it in any other way, then you discover that you won't be able to get 9. For example, if you try to match A1 and B1 first, now you won't be able to get both of these. You'll only be able to get one of these, and so on. Okay, let me go to this one first. Okay, so here you have this ICPC team selection. You have a bunch of people characterized their strength, which is a number, and you want to maximize the sum of all the team's performance. The team consists of 3 people, and each team is equal to the median of the team members. So the result of the second best student. Okay, and the question is, how do you want? So let's look at this: 8, 8, 6, 9, 10, 9. You want to split it up into teams of 3. So in this case, there are only 2 groups, 3. And within each group, the score or the value of that group is the second best person. So 10 has to go with somebody. So I'm going to put 2 groups. 10 has to go in somebody. Okay. Now, the weakest person actually doesn't matter, because you only care about the second best person. So if the weakest person doesn't matter, you want to put the weakest person with this one. So, and then you want to put something here. And in this case, if you put 9, the second biggest one, then this would sort of have the best possible team. And then you just repeat. Okay, so we've got 10, 6, and 9, and then put 9, 8, and 8. So the sum, it's 17, and that's the total strength. And there's nothing you can do to make it any better. So why? Right, so imagine that you do this. So let's imagine So you sort everything. So the way it works that we're going to do this is to sort everything. Let's say how many? So let's be multiple of 3. So let's make it 30. So 27, 28, 29, 30. And what we're saying is that the first team that we're going to form is the top 2 plus the bottom 1. And then the next team that we're going to form is the next 2 plus the second bottom 1, and so on. Okay, and the strength of each team is the middle one, and we're going to add up all of them to be the best possible sum of teams. Okay, so why is it going to be the best? Right? So imagine, so if this second best is not in the same team as the best, so I don't know, you put it somewhere else. So let's say here, and this one goes here, then this 29, the second best one, will be the best of that team and will no longer be part of the sum. And you just replace something with, let's say, this one that is smaller. Okay. So if this second best number is not going along with the biggest one, that means it must be something else that is not being used. And when you swap into here, you will increase the total sum because you now increase the sum of that team. And when you put in something that's smaller, that number was never going to be used to begin with because it was the biggest, second biggest. So when you put in something smaller, you may or may not increase this team as well. Okay. But the point is you will definitely increase this and you will not decrease this. And therefore, if the second best is not with the top one, you can put it in there and you will make it slightly better. And then you can carry out this logic throughout, and you can then say that, okay, you just keep on picking the second best one until you run out of teams. And this is what is called greedy algorithm. You sort the strength and then you go in a certain direction, whether you consider things from top to bottom or bottom to top, largest to smallest, smallest to largest, and then make a decision that way. And the idea is, in this case, is that you sort it and you pick the smallest one and the biggest 2 to form a team. Right? So intuitively, why do you do that? Because the smallest one, you want to spread them out so that they don't really affect anything because you want to not count the small one. Okay, so if you understood or believe what I said, then the code is not too bad. Okay, so in my main, I just go through all the cases, and for each case I call solve. And then in solve, I read n. I have a vector of 3 times n because if n is the number of teams, 3 times n is the number of people. I read them all. I sort it from biggest to smallest. And then here, this is a little bit of indexing that you have to, I mean, you can do it this way or you can do it in other ways. But basically here, it just counts the second top one. And then as I increases, it skips down by 2. So every second one from the top, that's the second best of the remainder. And I do it n times, and that's the answer. And in this case, I don't need to use long. Integer is good enough. Okay. The last problem is the one that requires the most knowledge, I guess. Find poly. You have a bunch of line segments in 2D plane, and then you have these things called geometric figure. That means that basically, if you read it all, it's basically everything's connected to each other. And then a polygon is a geometric figure for which it's possible to trace a path from some starting point, some endpoint P and ending at P using every line segment exactly once. So here, for example, all these are connected. So they're figures. C and D are not connected even though they intersect because the points, the line segment they give you don't actually intersect at endpoints. So you don't care about the intersection that are not at the endpoint. So same thing here, B intersect itself, but you can trace from one spot all the way back to itself. So that's a figure, sorry, a polygon. And then the G, it's not a polygon, even though it's a figure, because you, wherever you start, you'll get stuck. You will never be able to get back to the original starting spot. Okay, so they're basically, and then they give you these segments, which are coordinates. Connecting two pairs of coordinates is between 0 and 99. So there are 100 x and 100 y coordinates. At most 200 line segments, blah, blah, blah. And no line segments will be of length 0, so you don't have to worry about it giving you two endpoints that are exactly the same. Okay, so you get this kind of thing. You do have to figure out how to parse this, I guess. Why are the different semicolons? Semicolons are just, they can be any separators. So the semicolon is separate to actually the semicolon, the comma, and whatever, doesn't really matter. So actually one of the first things I did, where do I have this? Sorry, let me just find my code. So I have my separator, which are brackets, comma, and semicolon. I read the lines and I concatenate all the input together. And the first thing I do is I just any character that's separator, I just convert it all to space. So I don't really care. I always know that comes x1, y1, x2, y2, and just repeat it. So I convert it using a string stream, and I just keep reading x1, y1, x2, y2. Okay, so that's how I handle the input. But let's talk about what I'm actually doing. Okay, so I know that my grid, it's going to be between 0 to 99 in both directions. So what I'm going to do is I'm going to represent each of these as a node in a graph. Okay, because when somebody tells me that there's a line, I don't know, from 0, 0 to, I don't know, 1, 2, like this, then that means there's an edge connecting these two nodes. Okay, why am I using graph? Because to answer the question of whether I have a figure, it's basically asking how many connected components I have. So I'm just using these as nodes, and then I'm connecting them. I'm drawing edges. If there's an edge, they tell me there's a line connecting these two endpoints, and then I'm just going to see how many connected components there are. And if you're familiar with graph, you can use any of the ways. You can use adjacency matrix. Well, actually, in this case, it's not good. You can use adjacency list. And then so this is no good. Why? Because there are up to 10,000 vertices, but the number of edges, it's I think less than 200 or something like that. But small number of edges, it's not fully connected, so the adjacency matrix actually will be use up too much space. So you want to use adjacency list perhaps, and then you use one of the kind of algorithm to find connected components. For example, DFS, BFS, choose possible ones. How do you convert these coordinates into a actual node number? Maybe you can just do a row major representation. So you start from 0 to 99 on the row 0, and then next one is 100, 101, 102, and so on. So if you have x and y, you can convert it to x times 100 plus y, and that will convert a coordinate into an x, just a number from 0 to 9999, and that makes it easier to then use any kind of graph representation. I did not do any of this. I mean, I do that conversion, but I did not use the JSON list. I did not use DFS or BFS. I used Union Find that we talked about before. That's another way to figure out how many connected components there are. Doesn't really matter. You can use any one of them. That's fine. Okay, that will solve your problem of figuring out how many figures there are, but you have to worry about polygons. Polygons are things that you can come back. You can start from somewhere and then trace until you get there, get back to the start. Now, one of the things that it didn't really say, but if you read carefully the description, even though this is not technically a polygon if you read any math textbook, this is a polygon by the definition here because you can go like this, trace all the edges, and go back to the starting point. So if you read the description, a polygon is a geometric figure S for which it's possible to trace a path from some endpoint P and ending at P using every line segment in S exactly once. Oh, wait, when visiting each point other than P exactly once. Okay, so it does. Okay, so the what I just draw is not good. So this is not good because I visit this more than once. Okay, so forget about that. So what's going on then? The only way that can ever work is that every time you go in, so when you're tracing, every time you go in, you must be able to come out, except when you're starting, and you can never go in again. So what does that mean? That means that every node must have exactly two edges touching it. You go in, you come in, you go out, and you can never come back in again with another edge. So as long as all the degrees are even and it's connected, then the only way it can be is a polygon. So that's what I'm going to check, is that the degree of everybody is 2 in the figure. How do I do that? Well, it's fairly easy because when I add edges, when I know that there's an edge from 0 to 0, 2, I also have in each grid location a count of how many edges are touching it. So I just increment that so I can keep the degree, and then I just check the degree at the end. So let me just show you the code. I have this function called index, which is, take the index and convert it with the same formula I just show you. My graph is an adjacency list, I guess. A vector of integers with each location. And so when you give me x1, y1, and x2, y2, I convert to the node index u and v. I push back both ways. So my adjacency list has one more things. And the list and the size of the adjacency list is the degree. I use union find to merge them. And then I have this other array to keep track of which location actually has any line in it, because I have 10,000 points. Not all points will have line segments touching it. So I just ignore the ones that are not touching it. And then I just say at the beginning, at that index, if there's a point, I'm just going to assume that the polygon is okay. There's a polygon there. Okay. Now to count the component, all I'm doing is basically look at, for each point that is actually used, I look at the union find result, and if the label of union find is exactly the same as the index um, of that point, that means that it's a representative of that group, and there's exactly one for each group. So I count them. Otherwise, if it's not part of that, then it's not. I'm just going to set that polygon index to be false. So I will only set the polygon index to be true if it is exactly the representative. And then here, all I'm doing is I'm just saying for each node in the graph, I check if the degree is 2. And if it's 2, then I use the bitwise, logical AND equal. So what that means is that if the polygon at the polygon flag at the label was false, then it doesn't matter what this does, it's still false. But if it's true, then it will remain true if this point has degree 2, but it would get set to false if it's not degree 2. Okay, anyway, you can look at this code. All of that is on my GitHub repository. So please have a look. And I guess we'll take a break until school starts. And please watch out for the announcements. And we'll get back in person. Okay. Let's stop the recording. See you later.